Hello everyone, I'm here to present our work on tuning hyperparameters of anytime planning, a meta-reasoning approach with deep RL. This work was done with my colleagues Justin Svegliato, Samir Nashed, and Shlomo Zilberstein at University of Massachusetts Amherst. What are anytime algorithms? They are a class of algorithms that compute a suboptimal solution quickly and iteratively find better solutions. They are good for real-time planning because depending on time availability, they can be interrupted at any time to act on the latest solution. Every execution of an anytime algorithm has a performance profile, that is, how the quality of the solutions improve with time. Considering that in the real world there is a cost associated with execution time as well, there is a combined utility called the time-dependent utility that we should maximize. In other words, there is an ideal stopping point that strikes a balance between quality and time. And determining that point is challenging because the performance profile is not known in advance. In recent work, reinforcement learning was used at a meta level to interrupt an anytime algorithm as it executes. In our work, we apply deep RL to not just determine the ideal stopping point, but also simultaneously influence the performance profile itself by modifying the hyperparameters online. This is a white box meta-reasoning approach that considers internal features of an execution of the anytime algorithm. The reward function is designed to maximize the time-dependent utility prior to termination. In this work, we experiment with two common anytime algorithms, a general purpose search algorithm anytime weighted A star and a motion planning algorithm RRT star. We will now go through each one of them one by one. First, let's review anytime weighted A star or AWA star, which is an anytime variant of the popular heuristic search algorithm A star. It is based on the following design principles. First, the heuristic is multiplied by a weight greater than 1. As a result, the weighted heuristic becomes potentially inadmissible, leading to a suboptimal solution, but which is discovered faster. Then the algorithm continues the search to find more solutions after pruning the subtrees that cannot improve the solution. Ultimately, the optimal solution is guaranteed to be found. In this algorithm, the weight is a hyperparameter that affects the performance profile by providing a trade-off between quality and time. With a higher weight, better solutions are found in short term, compromising the long-term quality. By quality of a solution, I mean something inversely proportional to the cost of the corresponding goal node. This figure shows two idealized execution of AWA star on a particular problem instance. This shows that a weight of 2 is better in short term and a weight of 1.5 is better in long term. In general, the best weight depends on the problem domain, the problem instance, and urgency of the solutions. In earlier work, the weight was either tuned offline or adapted online heuristically, and we propose a principled meta-reasoning approach. Now let us define the meta-level MDP for monitoring and controlling AWA star. The meta-reasoner intervenes every delta time duration, say every 1/20th of a second. It intervenes to either interrupt the algorithm or modify the weight and continue. The state features include the quality of the latest solution, the time consumed so far, AWA star internal features such as statistics related to the open list, and search problem instance features, for example, the number of cities in traveling salesman problem, and maybe even system level features such as CPU usage. The reward function is simply the change in the time-dependent utility as a result of the meta-reasoner's intervention, so that the cumulative reward equals the final time-dependent utility, which is our objective. But the transition function is not explicitly known. As a result, we need a model-free approach like DeepRL. In this work, we use the popular algorithm DQN for the task. An episode of DQN corresponds to an execution of AWA star on one search problem instance. It looks as follows. It starts with initializing our search problem instance. Then the DQN picks a weight based on the meta level state, and continues the execution of AWA star for delta duration. After that duration, it observes a new meta level state and gets a reward which equals the improvement in the utility. Then DQN updates its policy based on feedback. This loop of adjusting, executing, and learning continues until the episode ends, which happens if either AWA star finds the optimal solution or DQN interrupts the algorithm if it believes that continuing the search is not worth an additional time overhead. We experiment with a setting where the time cost has two components. One is an exponential element, and then there is a mandatory deadline tau, which can be interpreted as adding an infinite penalty at the deadline. We experiment with 4 search problem domains and a deadline of 1 second for each. For each search problem, we train DQN for a few hours on random instances and later test it on another set of random instances. We consider a set of static baselines that used fixed weights and one popular dynamic baseline that decreases the weight after each solution. Both these baselines continue the search until the deadline. We compare with the baselines our meta-reasoning approach DQ and tau, which adjusts the weight on line and continues the search until the deadline tau. And we also compare the baselines with our ultimate meta-reasoning approach DQ&T, which can interrupt the search before the deadline as well. Here are the box plots for each benchmark problem domain. On the y-axis is the time-dependent utility. The various approaches are on the x-axis. In the box plots, the crosses denote the means and the bullets denote the outliers. In terms of mean solution quality, different baselines are better for different problem domains. Our DQ and tau approach, however, which is shown in green, which tunes the weight dynamically per instance and continues the search till the deadline, performs equal or better than all baselines across the benchmark domains. And our DQ and T approach, shown in blue, which can even interrupt the search at a suitable time, outperforms all other approaches, as expected. These are histograms showing the distribution of every instance over the utility error for each of our meta-reasoning approaches for each problem domain. For a given instance, we define utility error as the normalized difference between the final time-dependent utility of our approaches and the final time-dependent utility of the best approach that always executes anytime weighted A star until the deadline. On sliding puzzle domain, the utility error for both of our approaches is 0 for more than 800 out of 1000 instances. This means that on a given instance, our approach is highly likely to either match or exceed the performance of the best baseline approach. These results are similar across the benchmark domains. The takeaway from this slide is that across the benchmark domains on a given instance, our approach is highly likely to either match the best approach or be the best approach. This is the learning curve for DQ&T approach on sliding puzzle. The green curve shows the average quality, the red curve shows the average computation time, and the blue curve shows the average time-dependent utility as a function of training episodes. The task of the agent is to learn to maximize the time-dependent utility. To do that, it appears that the agent initially learns to optimize the solution quality even if at the expense of computation time. Later, after about 7,000 training episodes, it learns to interrupt the search earlier in order to continue improving the time-dependent utility. This figure shows which features the trained DQN network is most sensitive to in decreasing order. It shows that the DQN agent pays most attention to the quality of the latest solution, the estimated difficulty of the problem instance, the current weight, the upper bound on the optimal quality, and the time consumed so far, and some statistics of the open list. Here is an example of meta-reasoning during an instance of grid navigation problem. This figure shows how the solution quality green and the time-dependent utility blue varies as a function of computation time during this instance, and shows how the meta-reasoning agent adjusts the weight in orange. The dotted curve corresponds to DQ and tau approach, which executes the search until the deadline without interrupting. As a result, despite a good final quality, the time-dependent utility ultimately falls due to the time penalty. However, our DQ&T approach, shown in solid curves, realizes this earlier and interrupts the search. Now let's move on to RRT star, which is a motion planning algorithm in continuous state space. This is an animation of the algorithm being used for path planning from a start point to a goal point navigating through obstacles. The algorithm fills the space by growing a random tree and finding the shortest path through that tree once the tree connects to the goal. To grow the tree, a branch is grown in the direction of a randomly sampled point from free space. As the tree grows further, shorter paths are discovered, and the algorithm ultimately converges towards the shortest path. This makes RRT star an anytime algorithm. In this work, we consider RRT star with an adjustable growth factor and an adjustable focus region. The growth factor limits the size of new branches. The focus region biases the sampling and growth of the tree. This animation visualizes the effect of having a focus region and moving it around. We can use meta-reasoning to adjust the growth factor and move around the focus region in a principled manner. The details are as follows. We consider a contract setting where there is just a hard deadline and no other time cost. The actions are to move the focus region up, down, left, right, or adjust the growth factor. The state features include the quality, the time, RRT star's execution specific features, and map features. The rest of the details are same as were in AWA star. This figure shows the utility versus computation time averaged across episodes for three approaches. Vanilla RRT star with a small growth factor, vanilla RRT star with a large static growth factor, and RRT star with adjustable growth factor and focus sampling using deep RL. Our meta-reasoning approach clearly leads to better average utility by the end of the deadline. This is a visualization of DQ and meta-reasoning for adjusting RRT star on one particular example episode. These are 4 snapshots taken at different times in the episode. It shows how the meta-reasoner moves the focus region around to guide the tip of the tree to the goal node. This helps RRT star find the first solution quickly. After this, the meta-reasoner favors the center of the map to refine the path, which is not shown here, and ultimately outperforms the baselines on this map. To summarize, we propose a meta-reasoning approach to optimize both the hyperparameters and the stopping point simultaneously for anytime planning. We propose using deep reinforcement learning to carry out the meta-reasoning process. Our approach is general purpose and decision theoretic, which means that it optimizes the final time-dependent utility prior to termination. Our experiment shows that our approach leads to good results on RRT star and across domains on anytime weighted A star. Thank you.